So, whenever we were introduced to arithmetic, one of the first things we did was add numbers together. So, we had things like 2 plus 2 is 4. And then things like 2 plus 2 plus 2 is 6. Or 2 plus 2 plus 2 plus 2 is 8. But when we reach a certain point, it gets a little bit repetitive to just write 2 plus 2 plus 2 over and over. So what we did was we rewrote these things as 2 times 2. And then we rewrote 2 plus 2 plus 2 as 2 times 3 because it happens 3 times. And then on down the line, we wrote the third line as 2 times 4. And this multiplication is what we use to avoid having to add 2 to itself that many times whenever we need to do a simple sum. So, even that someday carried us on for a while, but wasn't enough forever. So let's say 2 times 2 is 4, but we want to get to 8. Sure, we could do 2 times 4, but assuming that we don't exactly know what numbers we're working with, say something just doubles 3 times, we'd write 2 times 2 times 2 is 8. And in the same vein, if it doubles again, we'd write this equals 16, and so on and so forth. But eventually we'll run into the same problem because we still have to deal with numbers that are larger than we would like to deal with by writing out these kinds of products. So what we decided to do was something similar. Instead of just multiplying, we decided if we put the number here, it represents repeated multiplication, and we call it an exponent. So 2 to the third means 2 times 2 times 2, and so on and so to the fourth. So the next thing that we are going to do is try to undo these operations. So over here, the way that we can cancel a 2 times 2 is we can divide it by 2. So 4 over 2 is 2. That's kind of undoing that multiplication. Now we have, hold on a second. We have 4 over 3. Oh, whoop, my bad. 6 over 3 is 2. And 8 over 4 is 2. And in the same way, you may be used to seeing this already, we have the square root of 4 is 2. The third root of 8 is 2. And the fourth root of 16 is 2. Now, what these roots represent are like division, but for exponents. That means that instead of saying, what number did we add to itself 4 times to get 8? We said, what number did we multiply by itself 4 times to get 16? And that's all fine and dandy, but when it came to multiplication, we were able to do it another way as well. So we had the choice to divide by the 2 here. Well, I'd say the 2 here, because I guess 2 times 2 is going to be a little redundant. You have the choice to divide by the 2 or by the 3, and we're going to get a perfectly good answer either way. And division is just going to work nicely for us to help us to get that no matter what we do. So like 4 over 2 is 2. 6 over 2 is 3. And 8 over 2 is 4. But I can't do the exact same thing when it comes to the exponents. Sure, the square root of 4 is still 2, but the square root of 8 is not 4. The square root of 8 is actually a really inconvenient number that looks like 2.828 something. And then the square root of 16, instead of going to 8, or even to 2, is just going to be, um, yeah, that is going to be 4. So like square root of 16 is 4. So we end up in just kind of a weird situation. Actually, by the way, 16 happens to be a particularly special case where the square root is 4 and the fourth root is 2. That might not have been the best example. If we were going to use something like the square root of 25 is 5, but the fifth root of 25 is most definitely not 2. What we're trying to explain here, though, is that taking roots like this is not going to be sufficient for getting the 2 or the 3 out of 8. It'll only give you the 2 when you take the 3 root. It doesn't give you the 3 by taking the 2 root. So there has to be another way to undo these exponents that is going to work for us in that case. And in fact, there is. There's an operation where you can say operation of 8 equals 3 when you plug in the 2. There's an operation that says operation of 16 equals 4 when you plug in the 2. That can take this expression and just get the 4 out of it. And what we call that is a logarithm. That's going to be just a word you'll have to remember, or at least log. So instead of these question marks, what that actually looks like is the log with a little subscript 2. I'm going to erase this because it kind of looks like a 1 and rewrite it. Of 8 is 3. Log base 2 of 16 is 4. And so on up the line as far as we're going to take this. Now, from here, we have a little bit of an inconvenience where we have a bunch of different ways of writing the same thing. We could say log base 2 of 8 is 3, and that's going to be the same as writing 2 to the third equals 8, and that's going to be the same as writing cube root of 8 equals 2. Now, in all of these cases, they all represent the fact that 2 times 2 times 2 is equal to 8. But they all look very different. And a little later on, we're going to address a way to make that a little nicer to handle. But for now, I just want you to recognize that these are all the same statement. So what we're going to do is actually set up an equation and see if y'all can translate from one to the other. So let's say we have 3 squared equals 9. Then we wanted to write it in terms of logarithms. That, you may be already ahead of me, but if we're just going to take this arrow, which doesn't really change the value of the expression, but only the way we write it down, we'll end up with something that looks like the log base 3 of 9 equals 2. And that's going to be the same as the square root of 9 equals 3. So in these, I'll write down a couple of examples to see if you can translate between them. I'll work one or two with you, ask you to do a couple more, and then I will show you a nice way that you can actually look at these that kind of unifies them. So what we're going to do is, let's say um, x to the third equals y. That we can rewrite in log form by saying log base. So again, we're going to take this base here and set it as a subscript to the log x of the one on the right side of the equal sign gets to be the other part of the log expression. Log base x of y equals, here comes the exponent. And then we'll write it as a radical where we know that the radical sign is going to show up somewhere. And what we get is the one on the right side of the expression from the log gets to go inside the root here. So the third root of this number inside this part of the log expression, so the third root of y equals the one we have left over, x. And the same is actually going to be true if we have expressions that don't just look like numbers of variables. We can have entire equations be the argument for this function and still translate it very nicely. By the way, I'm going to circle that as a 1, that is a 2, this is a 3, just so that we can have those to copy going forward. And let's see the fourth one. We have x plus 4 squared equals y plus 1. How are we going to handle this? You can pause the video and take a minute to think this through. Finally, we are going to translate this the exact same way that we have been. It's not going to line up perfectly because the expression's a little longer, but let's turn this into a logarithm function. We will have the log base x of y is going to be log base. We put this entire expression in that function because that's the part that's getting raised to a power, x plus 4, of the guy on the right is equal to the exponent that we used, which in our case was 2. And then finally, we'll translate it into a radical one. We have, the second root. Usually the 2 is assumed here, but because we're working with logs and translating things, it's going to be best to just write it for now. When you get more comfortable with this, you won't need to write a 2 on a square root, but for now it's going to be a little nicer. So it's going to be the square root of y plus 1. It's going to be equal to x plus 4. So now knowing all these things, I'll give you all a couple of problems to work on your own, and then I'll share a little way that can make this a lot nicer. So let's see, number 5. Let's say x plus y to the third equals 5. I want you to translate this into a logarithm expression and into a radical expression in the same way that we just did the first 4. How about number 6? Log base 5x plus 1 of 2y equals 4. And then 7 is going to be, oh, also I want you to translate that into an exponent and a radical expression. Finally, I'll have you translate a radical, which is going to be square root of 5x plus 4 equals 3y. So you copy down the 4 that I did, and then you do 5, 6, and 7 in the same way. Before I let you go, I'll show you one last thing that makes logarithms a lot nicer to actually deal with and kind of unifies them into one expression instead of three ways of writing down the same thing. And that's going to be what I like to call the triangle of power. What we can do, instead of writing these three equivalent expressions, we have one underlying statement that 2 times 2 times 2 is equal to 8. So that means that 2, our base, is raised to the power 3, our exponent, giving us 8, our result. And what we can do to represent one of these statements instead of all of them is we can erase the part of the triangle that appears on the right side of the equal sign. So let me actually move this triangle a bit so that we have more room to do what I'm about to do. We're going to stick this one here. And this expression here represents the triangle with the 2 and the 8 on it because it equals the 3. The triangle itself actually represents the number that's left off the triangle. So the 2 and the 8 at the bottom represent that the log base 2 of 8 is 3. The 2 and the 3 on the left and the top represent that 2 to the third power is 8. And finally, leaving the 3 and the 8 on the triangle represents that the third root of 8 is equal to 2. But they all represent the same underlying statement that 2, 3, and 8 share a triangle in this way. Feel free to use this kind of thing on your notes because it actually helps me whenever I'm working problems like this. Even though whenever you run into these problems in problem sets, they're not going to show you this triangle. But I would definitely recommend using it because it helps me understand them and keep them straight in my head and on paper. So you go ahead and copy down the 4, do 5, 6, and 7, give the triangle a try, and I will see you next time I see you.